Okay, so here we are at the third recitation. And today we're going to start with any general questions that people have about stuff that Zach's been talking about. Then we're going to go over how to put things into quadratic forms, why we see them so often, how to work with them. And then we're going to spend most of the time on dealing with KKT conditions or optimality conditions for optimization problems. And then lastly, I'll go through the augmented Lagrangian solver for QPs that you're gonna have to write in your homework. This is homework one that's due next Thursday. So I guess first part is are there anything that Zach has mentioned that you feel like could have been clearer, or maybe you want to see one more time, or you have like some follow-up questions on that you feel like a lot of other people might also have questions on? Um, if not, no worries, but if you do, it'd be a good time to go through it right now. So you can just put something in the chat if something comes to mind. Mhm. Okay, so the first question is how do we choose a good merit function? So this is a good question. So merit functions, this is really tricky. This is kind of the art of non-convex optimization is how do you choose a merit function appropriately? So when we're talking about merit functions, we're talking about we have some general, we're trying to solve for x, and then we have some step delta x that we computed using some method. So we have a step direction, and now we want to figure out how far do we step in that step direction. And we actually use that. And so what we're looking for is, x of k plus 1 equals xk plus alpha delta x. And usually when we do a line search, what we're saying is that there's some merit function, and we'll call it phi, and we want phi of xk plus alpha delta x. We want this to be less than or equal to, okay, strictly less than. And so this is like the main criteria. When we're doing a line search, we're looking for this. But this assumes we have some merit function. And so what Zach has talked about is for unconstrained problems, you can use just the objective function to make sure that you're lowering the cost of the problem. Alternatively, you can use like the Armio line search, which just uses some gradient information to make sure that your step is actually doing what your linearization says it should be doing. And then when it comes to constrained optimization, there's like a whole art to this. So line searching is like the most critical part of getting non-convex solvers to converge. And usually it takes a ton of tuning and lots of different penalties and heuristics to do so. So like a very common one is if I was doing constrained optimization, I may do, my merit function. So if we had min x, f of x, such that c of x equals 0, one possible merit function that people use is you could have p of x equals the cost, and then we have some penalty, and then, whatever norm you want to. So like you'll see people use the L1 norm. And so this, again, I kind of just made it up out of thin air. It's not like the obvious choice, but there's tons of different merit functions you can use, and they all work differently on different problems. So usually if you have a problem in mind, you can tailor a merit function that works very well for that to get nice, fast convergence. Alternatively, if you use a solver like IPOpt or SNOPT or something, they have very sophisticated line searches in there that use their own merit functions. They also use filters. You can look into filter line searches. They're a little different. But all this to say, you will not be expected to come up with your own merit function. These things exist. We won't use them in this class because we'll just kind of give you the merit function that seems appropriate. But just know that there are many that are out there, and they usually involve some balance of the objective function and some sort of constraint violation. And the idea is that not all of your steps are going to decrease the cost. Some of them may increase the cost, but decrease your constraint violation. In that case, maybe we want that step anyways. This is why like you can also use like the augmented Lagrangian itself as the merit function, and that actually works nice. Does that answer your question? All right, anything else? In that case, we're going to move to quadratic forms. So quadratic forms are super important because this is what we want everything to be in. This is what we give you stuff in. And knowing how to manipulate these quadratic forms is super important. So what I mean is that I have some function, f of x, and just make it look like this. So this is a quadratic form. I didn't say anything about like this having to be special or whatever. Just anything that is in this is a quadratic form. And the first thing to note before we get into this is that here we have a constant term. When we are minimizing an objective function, we do not care about the constant terms. They don't change what the minimizing argument is. So the solution x that would minimize this function does not care what this is. And the reason why is that when we go and take the gradient of this, the constant vanishes. So in general, sometimes we'll show this r, but oftentimes we'll just kind of omit it, and that's fine. We don't care about constants when minimizing. Okay. So now I'm going to go through, for those of you that are maybe like a little rusty on your general, like, matrix manipulation kind of stuff, we're going to go through kind of like the three things that you have to know. And then with everything else, you can kind of work it out. So here are the three. So the first one is that if I have A times B times C, and these are all matrices, and I transpose this, what I get is, if you remember, I flip the order of everything and I transpose everything. C transpose, B transpose, A transpose. So that's the first thing. Whenever I see these matrices that are lined up like this, I can always transpose it and just transpose everything individually and swap the order of everything. Now, the second thing is that what if I'm dealing with a scalar? So what if I have X transpose A, B, and I say this is, this is a scalar. So this happens when it's, these two vectors the same size, and then here we have a square matrix. So if I have this, very importantly, what I can say is that if I transpose a scalar, I get the same thing, right? If I transpose the number 4, I get number 4. When I transpose a matrix or a vector, it, swaps the rows for columns. But if it's just one row, one column, it's just a scalar, transposing it does nothing. So this is equal to its transpose, which again, I swap the order and I transpose everything. B transpose, A transpose, X. So this is important. If I ever see a scalar, feel free to transpose it. Nothing will change. And the third thing is, imagine if I had this right here, AX minus B transpose. I can just apply the transpose to each element. So I can do apply it to this, apply it to this, and I can use the first rule in this. So when I apply my transpose to this A times X, I have to swap the order and transpose things. So I get X transpose, A transpose, minus B transpose. So here are just kind of three general matrix manipulation tricks that we're going to use kind of throughout this course, throughout the homeworks and everything like that. And, if you haven't done this stuff in a while, it may be good to kind of go through these, just look at them and like really make sure that you understand why they're true and that we can use them. And then if you want more, in the background section on the website, look for the matrix cookbook. This is the ultimate kind of linear algebra and general matrix. I guess like it's kind of like the authority on all the little matrix tips and tricks that you would use, but it doesn't actually derive them or prove them or anything. It just kind of lists all of them. So it's really nice if you are, fundamentally just trying to use these things and not quite like worry about, how we can prove them. This is not quite what you do in a class, but if you just want to use them, the matrix cookbook has everything you would need to do with matrices, all just written out in the form where you can go look something up in the index, find it right away and use it, which is super nice. Okay. So with these three tricks, now let's go through one example of putting something into a quadratic form. And so what we'll do is we'll take the least squares objective. So what if I had, my least squares problem says that ax minus b, the L2 norm of it squared. So if I'm saying this, if I want to minimize this least squared problem, I want to put it into a quadratic form. And the reason why is because once things are in quadratic forms, it's very easy to take our gradient of it, right? And take whatever derivative we want to. Once it's in the quadratic form, this is the easiest thing for us to deal with. We want to put everything into this form. So let's start with standard least squares. So ax minus b, this is equivalent to, again, if I'm taking the L2 norm of it and squaring it, this is the same as me taking the dot product of itself. So I'll throw 1/2 there just because that's what you normally see. And what this is ax minus b transpose ax minus b. And now we're going to start using these three tricks, and we're going to basically move this into a quadratic form that actually works for us. So the first thing we do is we're going to distribute the transpose over. This is rule number 3. Also, these 3 rules, these are not like official rules. It's just 3 things that I wrote down. So if you go like try to find like an equivalent 1, 2, 3 of here, you won't find it. But 1/2 x transpose A transpose minus B transpose AX minus B. And now I can just FOIL everything. And this gives me X transpose A transpose AX minus B transpose AX minus X transpose A transpose B plus B transpose B. So the first thing we learned is that we don't care about constants. So if this was an objective function that I was just trying to write in a quadratic form, which is almost always what we're doing, feel free to just remove this term. This is a constant. It does not change the minimizing argument of the problem. We can ignore that. So I'll just say constant. The second thing is that we're going to use the second thing right here, that if I see a scalar, I can transpose it. So if you remind ourselves, this is an objective function. It's a scalar. So this is a scalar. This is a scalar. And when I FOIL it out, every single one of these terms is a scalar. I'm just adding up numbers. So what does that mean? It means I can transpose any of these that I want to for whatever like convenience reason I would care about. I can transpose these. I can get the same result. So here we will do, we're going to transpose this. We're going to using the second thing right here. So we transpose this. We'll see something really nice happens. Now we have 1/2 X transpose A transpose AX minus B transpose AX. Now, if I transpose X trans, I know I'm saying transpose a lot, I'm sorry. If I transpose X transpose A transpose B, what I get is I get B transpose AX, which is the same as this. So these two terms, it look different. I can just transpose this. Now they look the same. Plus B transpose B. Now I can go add these things. So I say 1/2 X transpose A transpose AX minus 2 BTAX. And if you remember with our quadratic form, what we're looking for is should be our vector, our matrix, this, and then it should be a vector transpose times our matrix. So this is the canonical quadratic form. I want to put what I just wrote down into this form, and I'm almost there. I'm just missing this thing right here. Doesn't have the transpose on it. So what I want to do is I'll now distribute this 1/2. I'll do 1/2 X transpose A transpose A X minus 2. I'm going to use the first thing, so I'm going to swap the order of this. So the 2 and the 1/2 drop. So now what we do is we just take this, we do So you see how this is equivalent, sorry, this is equivalent to this. These two things are equal. And now I have it in my quadratic form. So what I see is that this is my Q, this is my little q, and then if I want to, this is my R. But again, I'm always free to just omit this because it's constant.
Can this constant be thought of as a bias term in machine learning?
I guess bias in machine learning is a little different. We can think, I mean, bias really comes from the idea of you have like an affine opposed to a linear. So there's like a constant term. But yeah, basically like what this would do is this would say, like if I told you to minimize a cost function, like, minimize the amount you spend on a car, and then I tell you that you'll get taxed $1,000 either way, that $1,000 tax does
Ah,
not change what the cheapest
okay.
car you can buy is.
Right, okay. Also, in those three rules that you wrote, the second one, did you forget to put a transpose on the left-hand side or in the second one? Yeah,
Yep.
okay. Okay,
Sorry.
cool.
Okay. So now we have this in our quadratic form. Why is this so useful to us? And the reason why is that if I have if I have things written out like this, and I want to take the gradient of this with respect to x, this gives me qx plus q. If I want to take the Hessian, it's just q. So you see how I can take like whatever function I want to that has just a bunch of linear and quadratic terms. And if I combine terms and put them into this, taking my gradient and Hessian is very easy. So in homework 1, what you'll do is you'll write an augmented Lagrangian solver. You can put the full augmented Lagrangian into a quadratic form and then just take your derivatives like this, and everything is super nice. So now let's look back at the least squares problem. So if this least squares problem, I'm saying, here are my terms. I now have, my Q, little qr, and this is going to bring us to our next section. I'm going to kind of do a little bit of a piggyback on this, but KKT. And so the way I'm going to introduce KKT conditions is I'm going to talk about kind of the three increasing levels of complexity. So we have unconstrained problems, we have equality constrained problems, and then we have equality and inequality constrained problems. And we'll kind of like build up our KKT conditions one by one, and so we can understand everything at once. So to start, we'll do unconstrained problems, and I'll start with the example I just gave. So if I have an unconstrained problem that just says min x of x, my optimality condition, this is basically me saying, in order for this to be a local solution, it needs to satisfy this. It needs to satisfy the KKT condition. In the case of unconstrained problems, this is just the gradient of the cost function with respect to the primal variable must be equal to 0. And this is, we did this like in high school when you have, a quadratic function, and I want to find this minimum right here. I want to find when this slope is flat. This is like the lowest point. And the same is true if I had like a maximum or something. So importantly, these are first order necessary conditions. So what does that mean is that it's necessary for a minima, but it's not going to guarantee that this is the minima. And there's the one huge exception to this is with convex optimization. With convex optimization, there are every minima is a global minima. There's just one, or is either a solution or a set of solutions, but there's always one global minima that is any local minima. And what that means is that for convex optimization problems, the KKT conditions, this is enough to say you've solved it. Once you find anything that satisfies this, It's not just necessary, but in the case of convex, it is sufficient. So I will add this. If convex, it's sufficient. Okay, so our first thing was we have an unconstrained problem. I want to find the solution for it. The solution is going to happen when the gradient of this function equals 0. So let's just do a super quick example of this least squares problem. So up here we said Q is equal to A transpose A. So if I take the gradient of this function here, gradient X of 1/2 X transpose A X minus A transpose B transpose X plus 1/2. This gives me A transpose A X minus A transpose B. So this was our quadratic form. This is how we take the gradient in Hessian of this. And then here is our actual gradient. And so if I set this equal to 0, now I just have to rearrange terms. Now I get A transpose A X equals A transpose B. These are the normal equations. This is how you solve least squares problems of the type that I wrote up there. And this is nice because this is basically saying like I didn't have to use any of the geometric intuition for least squares. I'm sure we've all seen this derived a few different ways. I would argue this is, to me, makes the most sense. Just take your cost function, write it down as a quadratic form, take your gradient, set this equal to 0, and then you get the normal equations. This is the first super quick example of the KKT condition for unconstrained problems. I'll do example. Now, the second thing, we're going to add some complexity to this. We're going to do equality constrained. And this we've already seen a little bit. So this is problems like this. Okay. So once we have this, now we're saying, okay, there's a constraint in the mix. And so what I'm going to do is I'm going to form my Lagrangian. And this is super important as far as different conventions because what we use in the homeworks and recitation and what you'll see in Boyd's book is different than what Zach will sometimes use in class, and it's different than some other books. There are multiple different equivalent ways to do this. What we're giving you right now is a way that will never fail you. This is like, in terms of the homework is consistent. This will always work given any problem. This is one of the correct conventions. If you want to stick with this and use nothing else, that's totally fine. So the first thing we do is that if this is our problem, we form our Lagrangian. And this is just saying L x lambda equals F x lambda transpose C of x. This is our Lagrangian. This brings us to our first constrained optimality condition. This is called stationarity. And this just says that the gradient of the Lagrangian with respect to x must be equal to 0. And this is just this right here. So we've seen this in class a few different times. The second thing is primal feasibility or primal and primal feasibility just says it must satisfy the constraints. So that's pretty straightforward. That just says C of x must be equal to 0. And I'll go ahead and I'll move this over to make it. So that's it. For equality constrained problems, our optimality conditions, the things that I'm actually looking for, trying to get to, is just these two equations right here. And what we saw last time was that, if we look at this, this is just a root funding problem. I can use root funding like Newton. I can use a root finding method like Newton to solve any nonlinear system of equations, or at least I can try to. And in this case, if I go write this down here, I'm looking for a primal. So I'll do primal variable is x, and the dual variable is lambda. So the primal variable, this is what I'm solving for. And then the dual variable corresponds to the constraint, and the dual variable is the same size as the constraint. So say this is, um, say this is n, and say this constraint or this dual variable right here, lambda, this is m. This also means that c of x so the dual variable will always be the same size as the constraint itself. So this is, a system of 5 constraints, then this will be a length 5 vector. So here's our primal variable, here's our dual variable, here is our Lagrangian. We take our Lagrangian and we minimize it with respect to x. So we take the gradient of this with respect to x, and then we just say that it must satisfy the constraint. And this gives us stationarity and primal feasibility. And I can use something like Newton to go ahead and solve this. I just have a normal system of equations. I want the solution to it, so I phrase it as a root finding problem, and I use Newton's method for root finding. And now is where it gets more interesting. So now the third case. So again, we keep like building up the complexity, but these are all the same things. So for unconstrained, because there's no constraint, the Lagrangian is just the objective function. So stationarity is technically this condition as well for unconstrained problems. So this is all the same. So what we're working towards, the full KKT conditions for inequality constrained problems, this works for everything. I'm just introducing it step by step in terms of things that we've seen before. Okay, so now I'm dealing with a problem that says min x f of x subject to c of x equals 0. And then now I'll do g. So this is our like, we can put any problem we want to, we can put it in this form if there's no conic constraints, which we won't deal with yet. But any problem that we would care about for optimal control, we can put into this form. And this is why general nonlinear programming solvers, so SNOP and IPOpt, they will just take things in a form that looks like this. Maybe not this exact form, but the idea is that I'm minimizing some scalar objective function. I have an equality constraint, and I have an inequality constraint. So now let's talk about the variables. So my dual variables here, I'm going to have, I'll use lambda for the dual variable that is going to enforce the equality constraint. I will use mu for the dual that will encourage or that will enforce the inequality constraint. So now I do, the first step is always write down the Lagrangian. And this is where we start to see some different conventions. And so I'm going to make it clear where we're using a convention versus what is like the only way to do something. So L is a function of the primal and the dual variables, f of x plus lambda transpose c of x plus mu transpose g of x. So the reason this is important is because when I wrote down this problem, I did less than or equal to. Sometimes Zach will do greater than or equal to, and that will just change the sign here and then change the sign in the corresponding stuff. You can always work out what convention is true if it agrees with the one that I'm about to write down. So for all intents and purposes, you should take the convention that I'm doing right now as truth and use this always in homeworks, in your project, everything. So this is our Lagrangian. And if I take our first condition, which says that the gradient of the Lagrangian with respect to x must be 0, I get the following. So first condition, stationarity, we've already seen this twice. Now the second set of conditions, primal feasibility, this just says the constraints must be satisfied. So just the constraints that I gave you in the problem, these must be satisfied. This is the primal variable x must be feasible. And then we get the dual variable must be feasible. And what this means is that mu must be greater than or equal to 0. So this does not apply to the dual variable that is associated with the equality constraint. So remember, for c of x equals 0, our dual variable was lambda. So in this previous problem, lambda could take any value. It could be positive, it could be negative. Oftentimes it will be both. One of the parts will be positive or negative. Lambda can take any value as long as it satisfies these two things right here, it's safe. Like we found a solution. Now for inequality problems, this dual variable for this inequality, this must be positive. And again, this is a convention because we chose this to be less than or equal to 0, because we chose this to be plus, like these conventions line up such that this has to be greater than 0. And so Zach, like he will sometimes do other things, but what I'm writing down is will always work for you. So just use this. But dual feasibility says that the dual variable that is associated with the inequality constraints, so g of x less than or equal to 0, this must be positive. Now, this last term is the most difficult to deal with in terms of how we actually solve these problems. And this is the one that kind of makes our lives difficult. And this is complementarity slackness. And what this is saying, I'm going to write it down in 3 different ways, and I'm going to write like which way I like the most. So way 1 is that the ith element of mu times the ith element of the constraint must be equal to 0 for all I. I'll just say. So, if the second element of mu is 3, then this element must be 0. So this encodes the on-off switching behavior. Second way I can write this, I can say mu equals 0, where this is the element-wise. So these two are identical. I'm just writing them down in different notation. What you'll sometimes see, which I personally don't like and think just serves to confuse people, but I will tell you it so you know to look out for it. The next thing you will see is mu transpose g of x equals 0. And this is true, but it's not that useful for us. So if this is true, if these are true, then this has to be true, right? Like if every single variable here is 0 or non-zero in the corresponding points, then the dot product of them must also be equal to 0. So you'll see these written out places. This is not that useful as far as like how we build solvers. We really want more information. The reason why is that this is, if there's m constraints, this is m different equalities saying, this must equal 0. This is also m different equations. And this is just one equation. It's just a scalar. So I don't think this is this useful, but it is true. And if I have found something, if I just want to use these optimality conditions to certify that a solution that I found is correct, I can use this and that's just fine. But to me, it's not that useful. Put a star here. Not super useful. Okay. So here's the full picture. Here are our KKT conditions. Let me just So if I write down a problem that is minimize f with respect to c of x equal to 0 and g of x less than or equal to 0, if I, for a convex problem, which means that f is convex, g is convex, c is linear, if this is a convex optimization problem, and if I find a solution that satisfies all of these, I found the global solution. I have globally solved this optimization problem. And what it has to satisfy is that the gradient of the Lagrangian with respect to x must be equal to 0. This is stationarity. The constraints must be satisfied. This is primal feasibility. The dual variable that is associated with the inequality constraints must be positive. This is dual feasibility. And then this complementarity slackness, this is the ugliest and most difficult part. And this is basically saying that if this constraint is active, so it's less than or it's equal to 0, I need to have a dual variable that enforces this because now it's basically an equality constraint. But if I have an inequality that is not active, so say it has to be less than or equal to 0 and this is 10, then I don't want this to have any value. So I'm going to draw like a simple example of this.
In this part, if the constraint is active, then mu can take any value, right? Or it will just be positive values.
So yeah, mu is always positive.
But in the case of that lambda example, in the previous case, in the equality
It can
constraint
take
part, you said
anything.
lambda could take any value.
Exactly.
So isn't that like the equality constraint in terms of the this? I mean, aren't they both the same thing?
Yeah, so this is a good point. So if we think about this, earlier I said that for constrained optimization, that dual variable for the equality constraint, so this dual variable lambda, I said this can take any value. And c of x must be equal to 0, so this lambda that enforces this can take any value. But then what I'm saying down here is that, well, what if for some elements of g, what if I'm exactly at 0, so the constraint is active? Then it kind of looks like that thing can be treated as equality. Now, the reason why this is always positive and the reason why this is a convention is because the solver will not do anything that does not benefit lowering the objective value. And if we think about how we minimize this Lagrangian with respect to x, you don't want this to cheat anyhow. So what you're saying is that by mu actually being positive always, it means I'm not going to artificially take any of these constraints and activate or inactivate them just to lower the cost in a way that's like cheating. So this is very nuanced. If you don't want to understand this, that's fine. Just say like, for inequality constrained problems, the dual variable for the inequality must always be positive. But the actual interpretation is that our Lagrangian, we're minimizing it with respect to x. So constrained violations should be raising the Lagrangian. And if we have a function g that can be less than or equal to 0, and it's equal to 0, I don't want the solver to be able to exploit that and lower the value of lambda any more than I can. Does that make sense?
Yes, I think so. Okay.
Yeah, this is like a very non-trivial like intuition that is not super critical for doing these things in practice, but it is super interesting. And the point you made is like totally correct. And that it's kind of weird that when the G is active, so it's equal to 0, it's kind of an equality constraint, but hold up, the dual variable can't take any value like it would for a normal equality constraint. That can be a little confusing. So here I'm going to look at say the optimal value has my G. Again, it must be less than or equal to 0, and say it takes this right here. The way I can think about this is that this constraint, so these two, and then my dual variable, what complementarity says is that if this has a non-zero value, then this must be 0. And if this has a 0 value, this can be anything. So anything. So the idea is that when I take these things and I take the element-wise multiplication, they must always be 0. Now, I think a super important intuition is what do we do when we actually go to solve this? Like, why are inequality solvers so much more complex than equality solvers? And it comes down to these conditions. So if I look at an equality constrained problem, what I said was that, oh, I write down these two conditions. I have just two equations, two unknowns, and everything is of the correct size. So I have two equations, two unknowns. I can use Newton's method to solve for a solution x and lambda that satisfies these. Nice. Now I'm going to look at the inequality case. It just got a lot more difficult. So here is one equation. So first I have three unknowns, x, lambda, mu. Now I have one equation here, one equation here. This is an inequality. This I can't put directly into a root finding method. It's just, it must be true, but I can't write this as an equation that I'm looking for the root for. So these two things, I can't really put in Newton's method. This I can. So ultimately, if you want a solution to this, it must satisfy this, it must satisfy this, it must satisfy this, but then also these two must be true. And because of this wrinkle, because I'm not just able to set up a nice root finding problem and turn the crank on it, the solvers are a lot more complicated. And so there's a bunch of different methods to solve these problems. Zach went over a few of them. For convex optimization, primal dual interior point methods are like the best for small to medium sized problems. If you want like high accuracy, active set methods there's a bunch of different ways to solve these, and they all are more complex than equality constraint solvers because of this right here. And this brings us to what we're doing on homework 1, which is the augmented Lagrangian solver for quadratic programs. So first, I'm going to write down one more time all the KKT conditions for a convex QP, which is what we're going to solve in this homework. Made of X. So opposed to writing AX equals B and G of X less than or equal to H, I just put it in the form that we wrote down the conditions in. So where it was some constraint equals 0, some constraint less than or equal to 0. But you can just, feel free to move these over if you want to. So how do I know this is convex? This is convex if all the eigenvalues of Q are greater than or equal to 0, which in math land means this is positive semi-definite. So it's S plus. If it's positive definite, it's plus plus. But for convexity, we just need positive definite. Okay. So now that I wrote this, I'm going to go ahead and turn the crank and just start working through the KKT conditions. So here's X, lambda, mu, 1/2, X plus Q transpose X, plus lambda transpose AX minus B, plus mu transpose GX minus H. So the first condition, stationarity, that says that the gradient of this Lagrangian with respect to X must be equal to 0. And this is QX plus Q. So first condition, pretty easy to write out. The next two conditions, again, are just primal feasibility. So this is stationarity. Next two conditions, primal feasibility. And then now we have dual feasibility, and then complementarity slackness. Okay. So for a convex quadratic program, if I can show that these are true, I have found the global solution to the problem. And there's like no other interpretation of that. So this is the convex QP that we're looking at, and we're going to use this over and over again in the class. We love convex QPs. The solvers are super fast. They're well understood. And you'd be amazed at the number of really complex control behaviors you can accomplish using a controller that is based on one of these QPs. So this is our like bread and butter modern optical control is QP solvers. That's why this is so important. That's why we're making you build a solver in your homework to understand it, to really understand that these problems are useful and how to actually, formulate the optimal conditions to understand these and use those to build a solver. So now for the actual solver itself, we're going to introduce the augmented Lagrangian, which I know Zach has gone through a little bit in class, using some slightly weird conventions. So we're going to like really spell out exactly the way that you implement this thing. So if I have a row right here, this means augmented Lagrangian. And this is just the Lagrangian. And then now I'm going to add some penalties for things. 1/2 ax minus b transpose ax minus b. This should be actually, I'll write down a little easier way. Rho over 2. And then for an inequality case, this is where it becomes a little gx minus h transpose I rho. And so what I'm doing is I'm putting quadratic penalties on the constraint violation. So for the constraint violation for the equality constraints, it's easy because it's supposed to be 0. So if it's 0 and the constraint satisfied, this term is 0. If the constraint is anything other than 0, this term will be adding into our cost or into our augmented Lagrangian. Now for the inequality case, it's a little trickier because here, some of these constraints, I want them to be 0 and not higher, and some of these constraints are going to be negative anyways, and it's fine. So it's important that we have this mask here. So this is equality constraints. So what does this actually look like? What is I row? So I row is a symmetric matrix M where so if I have M inequality constraints, I row, just looking at the dimensions of this thing right here, I row is going to be a symmetric matrix, just like a diagonal matrix with entries on the diagonal. And it's going to be the size of the inequality constraint. And the way that I'm going to do this in code is I'm going to do a for loop where I'm just going to say, and then if the ith value of the constraint is strictly less than 0, and the dual variable in the ith element equals 0, in that case, it's fine. It's like the constraint doesn't exist. The constraint's being satisfied, the dual variable is inactive, the constraint doesn't exist, so I'm not going to penalize this at all. So you do I row, I equals 0. Anything else? I get I row, I equals the penalty. So this is how we do I in code. Okay. And that is the augmented Lagrangian. So now how do we actually like go ahead and solve this thing? I'm just gonna write down the pseudocode because we only have 8 minutes. Write down the pseudocode, and there's a video that's also attached to the homework where I go over this again, but QPAL. I will initialize this with x equals zeros, lambda equals zeros, mu equals zeros, rho equals 1, phi equals 10. So this is the initial penalty. This is how much I'm going to scale the penalty up every augmented Lagrangian iteration. And for I equals 1, 2, and then we'll just put like, the max AL iters. So the first step is we're going to solve this problem. I'm going to hold all these constant. I'm going to minimize this with respect to x. And so what we do is that we use Newton. And this is super important because last year, tons of people made this mistake on the homework and they all lost points. So the first step is to solve I take my augmented Lagrangian, I hold x, lambda, and rho constant. Sorry, I hold rho, mu, and lambda, mu, and rho constant. I minimize with respect to x. So this is me solving an unconstrained problem. So if you remember, how do we solve unconstrained problems? Well, I want the gradient to be equal to 0. So the gradient of the Lagrangian equal to 0. And I want to just take Newton steps. And so what does that look like? That just means, and you don't need a line search for this. This just means xk plus 1 equals xk plus or minus. So do this until convergence. So step 1, solve this unconstrained augmented Lagrangian. Set the gradient equal to 0. Use Newton's method on it. Do this recursion. Don't have to worry about a line search, and do this until you get the x. And then step 2, update duals. And this is just and the last step. So these 3 steps should be super clear. First thing I do is I form my augmented Lagrangian with the current values of lambda, mu, and rho. I use Newton's method to minimize this thing with respect to x. And I iterate this, so it's a loop inside of a loop. I iterate this until the gradient of the augmented Lagrangian with respect to x is equal to 0. And this should take, 2 or 3 Newton steps. Next thing I do is I update the dual variables. This is where I add, the current violations scaled by the penalty onto the augmented Lagrangian. I do the same for the dual variable for the inequality constraint. The difference is that I make sure it's always positive by just clamping it. So remember, my dual feasibility says that mu must always be greater than or equal to 0. So every time I update, I'm just making sure it stays that way. And then I increase the penalty. So where people really missed points last year was people were taking 1 Newton step and then moving to step 2. But it's not enough to take 1 Newton step. You need to sit there and take Newton steps 1, 2, 3 times until you solve this unconstrained problem. So this is a loop for the main AL iterators. You will have another loop in here or another function or whatever you want to do. You will have another thing that actually solves this sub problem to convergence before updating the duals and updating the penalty. So it's an easy mistake to make. A lot of people made it last year. You will get all the points if you just follow exactly this. And then the last thing we'll do is check convergence. So when can we stop iterating? Like when we know, like, are we good enough? So we can check the constraint convergence. So, so the equality violation, this can just be, and there's tons of different, you can different norms you would use. Infinity norm just tells you like the largest absolute value. That's totally fine. Inequality violation, max, 0, maximum. So I wrote this down in Julia. So max, just like in NumPy, max is like an element-wise max of 2 arguments. Maximum tells you the maximum value of the vector itself. So to check convergence, I can just make sure that these two constraints are satisfied. And all I need to do is ensure primal feasibility. And the reason why is because if I look at my KKT conditions, primal and dual feasibility, this is what I'm checking. Dual feasibility is guaranteed when I update my duals, I keep them positive. And this is satisfied every time we do the step 1 minimization. So all this to say that if I want to minimize, if I want to make sure that the solver is done and I found my solution, I can check all the KKT conditions if I want to. Probably a good thing to do. Alternatively, I'm okay with just checking the constraint violations. And if the constraints in terms of the primal variable are satisfied, then I'm happy and the problem is solved. And this is the criteria that you will use for the homework itself.
In the pseudocode, what you told was to first minimize it and then check for the constraints, right? So won't that take us off the constraint and then pull us back onto it?
I'm sorry, I think your audio is not that great. Would you mind asking that question one more time?
Am I audible?
I hear you, yeah, it's just not super clear.
Just hold on. Let me connect to the Wi-Fi. Um,
So in the meantime, I'll answer. Will had a question in the chat that I missed, which is I understand the math behind different ways to write the complementarity slackness condition, but why are there different ways to write this? Is it personal opinion preference, or are some ways better pseudocode wise? So this is a super good question. So it is absolutely personal preference. You'll see this, which to me is a more specific and less expressive and less useful way to write down the condition. These two are actually included as, equations in primal dual interior point methods. So many solvers will operate on these. It's true. So if all I want to do is just certify that a solution is optimal, I could use this, but this gives me more information. And I think this is the way to go. This stands to do nothing but confuse people. And I kind of feel like if you're just trying to certify the problem or certify the solution as an optimal solution, by all means, use whatever you want to. But as far as actually understanding what these conditions mean and how they work, these two are, in my opinion, are much more useful. And then for a lot of solvers, they actually operate on these, and this is not useful. And like I said, the reason why is because this is, a set of M equations, set of M equations. This is just a scalar equation. So it's not super useful. Like it gives us strictly less information than the first two. This just says they must be orthogonal, which could mean a lot of things. But the orthogonality so orthogonality plus these two is the same as this. But I don't see any reason why we have to combine these conditions into one. I think spelling everything out very specifically is a better exercise.
Yes, what I was asking was in the pseudocode, why did we separate out the minimization part and the checking the constraint part?
Are you talking about step one?
And yeah, I think, mm, I think yes. But did we separate out step one from the other steps? Like, isn't this first minimizing what we have, and like what exactly is happening in the second step?
In the second step. So Zach has like a much more thorough rundown of this stuff in class. The main intuition you want to get from this is that augmented Lagrangian methods, they started out as penalty methods. And all penalty methods say is that let's throw penalties on the constraint violation and minimize unconstrained problems while we increase the penalty on this until we converge to a solution. And this works, but the penalty has to go to infinity to satisfy the constraints. And when the penalty goes to infinity, numerically, it's very difficult to solve this problem in, like in floats in a computer. So we don't want to have to set this penalty up to 0 to solve it. So a penalty method is also, I'll write down a penalty method for just a equality constraint problem. I'll stop the recording too.